Hey everyone, welcome back to Brainstorm. This is our Level 2 Algebra walkthrough. In this video, we'll revisit exponents and take a detailed look at exponent rules. But first of all, what actually is an exponent? Well, an exponent, or the power of a number, is a number which tells us how many times to multiply a base number by itself. Right, so for example, if I had 2 to the power of 3, then our exponent in this case is 3 and our base number is 2. Okay, and what this is telling us is that we have 2 multiplied by itself 3 times. So we've got 2 times 2 times 2. Now 2 times 2 is 4. So 2 times 2 is 4, and 4 times 2 is 8. So we know that 2 to the power 3 is equal to 8. Now, an exponential function is a function which contains an exponent, right? So, for example, we might have, I'll give you 2 examples of an exponential function. We might have the function of x, which is equal to 2 to the power of x. So this is just one example of an exponential function because we have a base of 2, and x is actually our power. So x can be any value of x, and the output of that function is going to be 2 to the power of that number, right? So if x was equal to, I don't know, 2, for example, then we would have 2 times 2. So our output would be 4. Another example might be the function of x is equal to 0.4 multiplied to the power, not multiplied, raised to the power of x. Now in this case, our base is 0.4. So our bases don't necessarily have to be integers per se. Now if I was to graph what these functions look like, they would look a little something like this. So let's look at 2 to the power of x first. So if I drew a number line, so these are my y and x axes. If you were to plot the points on the graph, I'm not going to do that, but I'm sure that you know how to do that. You would get a graph that looks like this. So it would look something like this. In fact, that's probably not a good example. Let's redo that. It looks something more like that, right? So as the values of x increase, we see that we get a rapid increase in our output, right? So as our input values increase towards infinity, our output values get closer and closer to infinity, right? So we see this rapid increase, right? So the increase here is significantly more than the increase down in this region here. Okay, if we looked at 0.4 raised to the power of x, if I redrew my axes, here, this graph would look a little something like this. So it will look, sorry, I'll redo that one. Not perfect, but it would look a little something like this, where we start off with a rapid decrease, right? So this region is decreasing very, very quickly. And then as we increase, so as our values of x increase, our values of our output get closer and closer to 0. So what does this tell us? Essentially, this tells us that exponential functions either are rapidly increasing or rapidly decreasing from some initial value. Now, if this was a little bit confusing, that's okay, because the standard doesn't really focus on defining the exponential. Rather, we're just interested in exponential manipulation only. But I'd feel bad if I didn't tell you what an exponential function actually is. Okay, so we have 4 rules or properties of exponents that we're going to take a look at. Now, we're not going to prove that these hold for every exponent, but I'll give you some examples to hopefully give you some intuition of why these product rules are what they are. These exponent rules are what they are. Let's look at the first exponent rule. This rule is called the product rule. Now we've already used some of these rules probably last year as well, but here we're going to just define them. So the first rule, the product rule. The product rule. Now, let's do an example. Let's say I asked you to compute 2 to the power of 2 multiplied by 2 to the power of 3. So compute 2 to the power of 2 multiplied by 2 to the power of 3. Well, if we wanted to do that, we know that 2 to the power of 2 is 4. And we know that 2 to the power of 3 is 8. So we get 4 multiplied by 8, which gives us 32. Now, compute 2 to the power of 5. So compute 2 to the power of 5. And if you want to do that, we would multiply 2 by, multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2. This is because we've got 2 multiplied by itself exactly 5 times. So this is what the exponent means. So 2 times 2 is 4, multiplied by 2 gives us 8. 8 multiplied by 2 gives us 16. And 16 multiplied by 2 gives us 30. And 16 multiplied by 2 will give us 32. Okay, so as you can see, 2 to the power of 5 is 32, and 2 to the power of 2 multiplied by 2 to the power of 3 is also 32. Is there some kind of relation or some kind of connection here? Well, there is, right? 2 to the power of 2 multiplied by 2 to the power of 3, if we added those bases, so if we added 2 and 3 together, we would get 2 to the power of 5, which is equal to 32. And so for any trivial base a, we are saying that the product rule is that we have any base a raised to the power of n multiplied by a to the power of m. This is the same as a to the power of n plus m. So this is a little neat trick that we've been using, I think even in the level 1 MCAT. So let's give it a go. So let's try and compute. Let's compute 3 to the power of 2 multiplied by 3 to the power of 24. So how are we going to do this? Well, 3 to the power of 2 multiplied by 3 to the power of 24 using our product rule is the same as 3 to the power of 2 plus 24. And this is equal to 3 to the power of 26. Now, if you have a calculator on you, I'm sure you can calculate that. I don't, so I'm going to leave it as this, but this is our final answer. Now, the second product rule, which is kind of based off that first product rule, so remember this is our first product rule, kind of coming off that, note that a to the power of n multiplied by b to the power of n. So in this case, we've got the powers are the same. Sorry, so this should be n. So the powers are the same, but we've got different bases. So as a result, what we can do is we can factor out that power. So this is going to be equal to a times b raised to the power of n. So if we wanted to expand this out, we'd just do a, we'll put the n on all terms. So we'd get a to the power of n multiplied by b to the power of n. Let's look at an example of that. So here I've got the simplify 34 raised to the power of b squared qy multiplied by 2 to the power of b squared qy. Now, if you remember our second product rule, it was that if we have the same power on both terms, but we have differing bases, what we can do is we can factor out that power. So let's go ahead and do that. So this is going to be the same as 34 multiplied by 2 raised to the power of b squared qy. Now, all we have to do is we just multiply our bases together. So 34 multiplied by 2 will give me 68 raised to the power of b squared qy. Now we can't get any simpler than that, so that's our fully simplified term. So that was it for the quotient. So that was it for the product rules. Now let's have a look at the quotient rules. So if I asked you to compute 2 to the power of 3 divided by 2 to the power of 2, what would you get? Well, we know 2 to the power of 3 is 8, and we know 2 to the power of 2 is 4, so 8 over 4 is equal to 2. Now, why don't you go ahead and compute 2 to the power of 1. Now, 2 to the power of 1 is obviously 2. So is there a relationship between this fraction here and 2 to the power of 1? Well, if you thought about it for a while, you might see that if in fact we subtracted this power from this power, we would indeed get 2 to the power of 3 minus 2, and this would give us 2 to the power of 1, which is equal to 2. And so for any trivial base a to the power of n over a to the power of m is the same thing as a to the power of n minus m, assuming that our base a is the same. So let's look at an example for that now. Let's say our e dot g, let's compute 4 to the power of 27 divided by 4 to the power of 24. So because our bases are the same, we can use that product rule here. Our quotient rule. We can use our first quotient rule. So that's going to give us 4 to the power of 27 minus 24, which is going to give me 4 to the power of 3. Now 4 to the power of 3 is equal to 64, right? And that is, just as a reminder, 4 times 4 times 4. So that's 16 times 4, which gives us 64 as required. Now, coming from that, our second quotient rule, which is a bit of a factorizing one, just like the product rule, if we have a to the power of n divided by b to the power of n, so we've got the same powers on the top and the bottom of the fraction, but the bases are different, we can take that power out. So we would get a over b raised to the power of n. For example, let's simplify 7 raised to the power of 42xyz over 49 raised to the power of 42xyz. So how do we fully simplify this? First, let's look at our fraction bit. We've got 7 over 49, so we can simplify that by dividing the top and the bottom by 7. So if I divided the top and the bottom by 7, 7 over 7 gives me 1 over 49 over 7, which gives me 7. But both of these are still raised to 42xyz. 42xyz. Now, look at our second quotient rule. We're saying that we've got different bases. So we've got base 1 and a base 7 here. So, as a result, what will we get? Well, what we can do is we can take out that power. So what we can do is we can say that we've got, this is the same as 1 over 7 to the power of 42xyz. Now, you may not consider this the simplest form because, as you know, 1 raised to the power of anything is still going to be 1. So we could have written this fraction as 1 over 7 raised to the power of 42xyz, right? And we can't go any further than this. So you might want to call that your simplest form. It's really up to you. Next, let's look at the power rules. So next we're looking at the power rules. The power rules. Now the power rules say that if we've got a to the power of n and we raise that to the power of m, this is the same as base a raised to the power of n multiplied by m. Okay, so that's interesting. So let's look at an example of this. Let's say I had 3 to the power of 2 raised to the power of 4. Well, this would give me 3 to the power, using our first power rule here, this would give me 3 to the power of 2 multiplied by 4, which is equal to 3 to the power of 8. So that's a nice trick that's going to be useful for us. Now, the next thing that we will need to consider is using square roots. Okay, so let's, in fact, generally speaking, most people know that if I take the root of some arbitrary number, let's call it b. This is the same as b to the power of 1/2, okay? This is the same as b to the power of 1/2. As a result, what we're saying is if we change these numbers here to n over m, so now if I had b over n over m, what we're saying here is that this is the same as the root of b to the n, and this is the nth root. So a bit confusing here. Essentially m is the same as 1 in this case, and n, sorry, my mistake. M in this case is the same as 2, so the denominator, and n here is the same as this top power here. So let's do another example since I mucked that up a bit. Let's change this into root form. So I've got 4, in fact, let's put a letter. Let's do x raised to the power of 7 over 9. Let's write this in root form. So the way we'll do that is we're going to put a root, and we'll put our base inside of that root. Now, the number on top of this fraction here will be the exponent of that base x. So here we've got a 7 as the numerator of our fraction, so that will stay as the exponent here. And then this is the 9th root of x to the power of 7. So whatever's in our denominator, it becomes on the outside of our root. If we wanted to go the opposite way, let's say I had the 4th root of x to the power of 3. Well, how would I put that into exponent form? We know that the numerator is this number here of our fraction, so we'll get x to the power of 3, and then the 4 is the denominator, so x to the power of 3 over 4. Finally, let's take a look at negative exponents. Negative exponents. Now, all this says is that if I've got b raised to the power of negative n, this is the same as 1 over b to the power of n. So we can write this as a fraction, and where the exponent becomes positive. Let's look at an example of that. Let's say I had b raised to the power of negative 2. This is the same as 1 over b squared. So you might have actually seen this in science. You might have known that sometimes we write m over s, so meters per second is the same thing as meters per second raised to the power of negative 1. Well, the reason for that is if we think of m over s, this is the same as s raised to the power of 1, and we can rewrite this as m multiplied by 1 over s to the power of 1. Now, if we wanted to make this on the top, so if we wanted to make the exponent negative, this would be the same as m multiplied by s to the power of negative 1, right? Because just using this form here, so s to the power of 1 is the same as s to the power of negative 1 without this exponent, without not being in fraction form, if that makes sense. So I've converted this backwards into b to the power of negative n. So b was our value of s, and n was our value of 1. Okay? So this is m multiplied by s to the power of negative 1. And that's why we write meters per second like this in physics, for example. Alright, let's look at some example questions. First of all, let's do an easy one. Let's say we wanted to fully simplify 25m to the power of 16 raised to the power of 1/2. So we're going to have to use multiple exponent rules in order to solve this. We probably want to deal with this overarching 1/2 here, right? So in order to do that, if you remember the rule which says if we have an raised to the power of m, this is the same as a raised to the power of n multiplied by m. Now this is only for exponents, right? So what we'd have to do is we'd have to distribute this raised to the power of the constant as well. So let me walk you through that. So what we would do is we would say 25. Now 25 is a constant, so we can't use any exponent rules, we just have to put the power onto that. So 25 raised to the power of 1/2 multiplied by m raised to the power of 16 multiplied by 1/2, because that is our product rule. So this here is this rule applied. Now what's 25 raised to the power of 1/2? Well, 25 raised to the power of 1/2 is the same as the root of 25, if you remember that exponent rule. So if you've forgotten what that was, essentially a to the power of n over m is the same as the root of m raised to the power, a to the n will be inside the root, and then outside the root will be that m. So this is the same as the root of 25 multiplied by m to the power of 8. Now the root of 25 is 5, so we get 5 multiplied by m to the power of 8, which gives me 5m to the power of 8. And that's fully simplified. Let's do another question. Let's say that we had 4 over 3a raised to the power of -2, and we want to fully simplify that, and we want to leave our answer with a positive index. What that means is we want our powers, or our exponents, to be positive. Okay? So let's have a look at how we would do this. So 4 over 3a raised to the power of -2. So what's the product rule say when we've got a fraction raised to the power of something? Well, we can distribute that power onto both the numerator and the denominator of a fraction. So what this will leave us with is 4 raised to the power of -2 over 3a, and this is in brackets, to the power of -2. Now, we need to make sure that we're leaving our answers with positive indexes. Okay, so one way that we can do that is, if you recall, we've got the rule that says a to the power of n is the same as a to the power of -n is the same as 1 over a to the power of n. So this is one way that we can make a negative exponent positive. So let's apply this to both the numerator and the denominator, and then we'll see what simplifies out. Okay, so let's look at our numerator. So we've got 4 to the power of -2. 4 to the power of -2. Applying our rule, this is the same as 1 over 4 squared. 1 over 4 squared. Now 1 over 4 squared is the same as 1/16. Okay, so our numerator is the same as 1 over 16. Now what about 3a raised to the power of -2? Well, using our rule, this is the same as 1 over 3a squared. Now remember, both 3 and a are squared. Okay, so don't make that mistake of just putting 3a squared with no brackets, because that's a different number. So we've got both the numerator and the denominator in positive exponents, and this has been fully simplified out. So what we've got now, if I draw an arrow, what we've got now is we've got 1 over 16 over 1 over 3a squared. Now this can be rewritten as 1 over 16 divided by 1 over 3a squared. And if you remember, when we divide fractions, we flip the second fraction and multiply it across. So what we get left with is 1 over 16 multiplied by 3a squared over 1. This gives me 3a squared over 16. This is the same as 9a squared over 16. Now, I don't think we can get any more simple than this, so this is my fully simplified answer. Let's do another example. Let's say that we wanted to fully simplify the root of 32 over x to the power of 5 cubed, and this is the 5th root of that. So let's fully simplify this and leave answer with positive exponents, with positive exponents. So all our exponents must be positive. So how are we going to do this? Well, let's look at if you remember our square root rule, or our root rule, we have a to the power of n over m is the same as the root of a to the power of n, and this is the nth root. So what we're going to do is we're going to take out different parts of this nasty looking thing and essentially convert it into our fraction form. I think that might be the easiest way to go about it. So what do we have here? We're saying that this is our base. So 32 over x to the power of 5 is our base. This is going to be raised to a fraction, and that fraction is going to be this number being the numerator of that fraction and this number being the denominator of that fraction, right? So this is going to be m and this is going to be n. So what we get left with is 3 over 5 as our exponent here. Now what we can do is we can go ahead and distribute out this exponent onto both the numerator and the denominator. So what we get is 32 raised to the power of 3 over 5 over x to the power of 5 raised to the power of 3 over 5. Now 32 raised to the power of 3 over 5, because you'll have a calculator, you can go ahead and calculate that, but this is actually equal to 8. And 8 over x to the power of 5, x to the power of 5 raised to the power of 3 over 5. Now remember, when we're raising some exponent to another exponent, we can actually multiply those exponents together. This gives me x to the power of 5 multiplied by 3 over 5. And what this will give me is x to the power of 15 over 5. So our denominator is x to the power of 3. So we ended up with 8 over x to the power of 3. Alright, let's look at one more example. Let's say I had a to the power of 10 over 4a to the power of 5, all raised to the power of negative 2. And we want to simplify it and leave our exponents positive. So we will say simplify with positive indices, or positive indexes. Okay, so how do we tackle this? Well, first thing we need to do is distribute this negative 2 onto both the numerator and the denominator. So we'll get a to the power of 10 raised to the power of negative 2 over 4a to the power of 5 raised to the power of negative 2. Now if we distribute these powers out onto both the numerators and the denominators, now 10 multiplied by negative 2 will give me a to the power of negative 20, because when we raise an exponent to another exponent, we multiply the exponents together. This is over 4 raised to the power of negative 2, because remember 4 is not a term, it's actually a constant. So 4 to the power of negative 2 multiplied by a to the power of 5 raised to the power of negative 2, which is the same as a to the power of 5 multiplied by negative 2. So that will give me a to the power of negative 10. A to the power of negative 10. So what we've got here is we've got both the numerator and the denominator as with negative indexes. Remember, we need to have positive indexes. So how do we do that? Well, you saw before that what we can do is we can use the rule which says that if I've got a to the negative b, this is the same as 1 over a to the positive b. Using that rule, we could have done the whole long way around, but as a quick side note, which I've proven just a couple examples before, what we can just do is we can just flip the numerator and the denominator around and then just make all the exponents which are negative positive and all the exponents which are positive negative, and that will work out just fine. So this is the same as 4 to the power of 2 multiplied by a to the power of 10 over a to the power of 20. If you're not comfortable with that, all we're doing, I just skipped all the steps, is we're just taking this rule here, we're applying it to the numerator and the denominator, and then we're dividing those fractions. So this is equal to 4 to the power of 2 multiplied by a to the power of 10. That is 16 multiplied by a to the power of 10 over a to the power of 20. Now this is the same as 16 multiplied by a to the power of 10 over a to the power of 20. Now what we can do here is we can actually, so if you remember our quotient rule, this tells us that if we've got a to the power of 10 over a to the power of 20, what we can do is we can actually subtract this 10 from this 20, right? So if we have a to the power of n over m, this is the same, sorry, if I've got a to the power of n over a to the power of m, well, this is the same as, and we're assuming that m is actually larger than n, this is the same as 1 over a to the power of m minus n. So I'm going to apply that rule right here, which says that we've got 16 multiplied by a to the power of 20 minus 10 over 1. So this is going to be equal to 16 multiplied by 1 over a to the power of 10. Now, if that doesn't make too much sense to you, I can just bring the powers up, but that'll give me a negative index. For example, if I still had a to the 10 over a to the 20, and I just do a to the power of 10 minus 20, this gives me a to the power of negative 10, which I then need to apply the positive exponent rule, which gives me 1 over a to the 10, which is the exact same thing. Now, if I set this equal to each other, this will give me 16 over a to the 10. I can't go any simpler than that, so this is our final answer. Awesome guys, thanks so much for checking out this video on exponents, and stick around for the next video. Cheers.